Alright, so this is problem 30.5, and it again deals with Faraday's law. So we're told that we have an aluminum ring of radius R1 is equal to 5 centimeter that has a resistance of 3 times 10 to the negative 4 ohms. So they're talking about this aluminum ring right here that's in yellow, okay? So it is placed around one end of a long air core solenoid, so this solenoid here, that has 1,000 turns per meter, so that's N is equal to 1,000 turns per meter, and it has radius R2 is equal to 3 centimeters. So the idea here is that when we have this current going in this motion here, we know that that's going to induce this magnetic field. If you use your right hand rule, the magnetic field due to the solenoid is going to be pointing in this direction. We also know from previous weeks that B is equal to mu naught times N times I, right? We're told that we have a current that is increasing at a rate of 270 amps. So current increases by 270 amps every single second. The idea here is that I is part of this magnetic field equation, right? And the idea is that we're trying to figure out how is the flux changing, because when we have a change in flux, according to Faraday's law, we're going to have an induced current, and that's what we want to figure out in A. There's a couple more things we need to talk about first, though. The one being this here. It says, assume the axial component of the field produced by the solenoid is 1/2 as strong over the area of the end of the solenoid as the center of the solenoid. It is saying, sure, this is normally what you use for B. Down here in the relevant region, it's going to be 1/2 that value. So divided by 2. That's the value for B that we are going to be using down here. And we know that it is uniform and it is only contained inside of this region, right? That's the next sentence. It says, also assume the solenoid produces negligible field outside its cross-sectional area. B is only along here. So let's go ahead and figure out what the current induced is inside the ring. This is A, and to get the induced current, we first need to find the induced EMF, where E, the EMF, is equal to negative d over dt of the magnetic flux, which here is just B times A times cosine of theta, because here we're just looking at this area here that is nicely lined up with our magnetic field. And we know here that cosine of theta is the angle between B and A, where A is the area vector pointing in the same direction as B. So that's going to go away. We know what B is. It comes from here, the solenoid, and the area is just going to be the area here. At least that's what it normally would be. The thing you have to be kind of careful about here is because this is saying how much flux do we have going through this region here. Normally you just add up all the magnetic field lines, right? The thing is though, the magnetic field lines are confined within this region. So here in yellow, I'm going to draw it around here, there is no magnetic field line. So there is no magnetic flux. So whenever we do this area, well, there's no sense in including this empty space area. It's just going to mess up our equation because there are no magnetic field lines. The only area that we can talk about here is this area because that is where the magnetic fields are coming from, like the magnetic field lines. So let's put all that together. We have E is equal to negative d over dt, and then we have mu naught times N times I over 2 times the area, where the area here is pi times R2 squared, right? Not R1 squared, R2 squared. Cosine of theta is equal to 1. Okay, so we have this, and then we say that E is equal to negative 1/2, and then let's just pull out all the constants. So we have mu naught, 4 pi times 10 to the negative 7 Tesla meters per amp. And then I'm just going to move this over here. So this is E. We have mu naught times N. N is going to be 1,000 turns per meter times pi times R2 squared, so 0.03 meters squared, and then times And then what we get here is di over dt. All I did was take out all the constants, so constants like that, take them out, and then I said, okay, well, we're taking the derivative of I with respect to time. Now, luckily for us, we're given what the derivative of I is with respect to time. It's 270 amps per second, right? That's this change. So here we say times 270 amps per second. Multiply all these numbers together, and we get the EMF is equal to negative 4.8 times 10 to the negative 4 volts. Okay, so that is our EMF, and we're of course assuming that this change is just a constant change with respect to time. So every second it changes by a certain amp. So now we have E, we can find out what the induced current is, and that's what we do in A. Current in the ring is equal to magnitude of E divided by R, the resistance. So this is Ohm's law, and then we just get 0.00048 volts divided by, and then, well, what's the resistance? And that comes from all the way up here, where we're told what it is. Plug those in, and we get 1.6 amps. Okay, so that is the current going through the ring. Now, where is it going? Could be the next question we ask ourselves, right? So the idea is here, this has a negative sign here, and we know that if I have this, I have a current that is increasing. The current is increasing, which means that every second, this magnetic field here is also increasing. So the flux going through here is increasing in this direction, right? So it's getting stronger and stronger every second. And we know that the current induced has to be such to oppose this motion. So we know that the current around this circle here has to be such to create or induce a magnetic field that is going in the opposite direction. So we're going to have B from ring. So then if we use a right-hand rule, we then know that the current has to be going in this direction here, right? So if it's going like this, where the arrow is going like this, we're going to get this magnetic field in the other direction to counteract this increase. So if my eye is down here, so we usually draw this out. I mean, this is kind of ugly, but this is like your eye, when you're looking at it, you see that it is going in the counterclockwise direction. Okay, so this is where the current's going, and we know what its magnitude is here. So next we look at B, which is saying what is the magnitude and the direction of the magnetic field produced by the induced current in the ring. Well, we already know what it's going to look like. We know that it has to be pointing in this direction, but what's its magnitude? We know here that the magnetic field from a ring is just equal to mu naught times I divided by 2 times R1. Where now we do have to take into consideration the actual dimensions of the ring here. And then all we do is plug in our numbers. So we get 4 times pi times 10 to the negative 7 Tesla times meters per amps times 1.6 amps, because that is the current that we have induced, divided by 2 times 0.05 meters. And this, the magnetic field induced by that ring is equal to about 20.1 microtesla. So again, the next question says, like, where is it going? And we already know where it's going, right? Because of this opposition that comes from Lenz's law, okay? So B ring is going to be in this direction to oppose the increase of this direction here. And that is it for the